All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 391. It is, in fact, the last class today. Your test is tomorrow. Apparently, there were still people who are confused about that. You know, we've mentioned it several times at this point. But today is the last lecture. So today we're going to finish up the syllabus. It's going to be very cool, very exciting, at least I think so. We are going to, also the test covers up to everything that we did yesterday. So what I'm talking about today will be technically given as bonus problems. So officially it's not really due, but it's not going to be like totally serious. It's going to be like a very cool kind of application that we're going to be discussing today. And it's just going to be a little addition to things that we've been talking about. But I think it's going to be a cool lecture. It is going to actually tie together a lot of things. It's going to tie together things that we've been doing recently to things that we've been doing since the beginning of the class. So we're going to talk about first order ODEs again, and inseparable and separation of variables and second order linear ODEs. And we're going to connect that to series solutions, and we're going to connect that to things that we've been discussing recently. And we're going to connect that to something even higher. We're actually going to talk about a PDE. So we're going to kind of wrap everything together. It's going to be a great lecture, I think, in my opinion. And it's going to be a poetic end, we shall say, to the journey that we've been on. So I'm very excited to get started. Let's actually get started. Here is the OneNote document, and let's jump right in. So we are going to do some technical stuff and some calculations, but it's not going to be terrible. And at the same time, hold on, something is giving me issues. Let me restart here. But at the same time, the lecture is mostly going to be of a conceptual nature. But every now and then we're going to come in and we're going to do some calculations, which individually they shouldn't be too bad. And individually you'll find out that there are calculations that we knew how to do before, but we are now going to apply them to a certain type of problem. So we are going to talk about the heat equation today, and the heat equation is actually a special type of PDE. So very important thing in physics, very important thing in engineering. It's talking about diffusion. Specifically, we're going to look at heat conduction in a metal rod. However, you can apply the concepts here to all sorts of things, like the diffusion of a gas through a room. That is going to be a higher dimensional version of this problem that we're going to talk about. We're going to talk about pretty much the one-dimensional diffusion equation, which is often called the heat equation because it's often envisioned in terms of heat being distributed through an insulated rod. And that is the ideal situation that was studied to kind of figure out the situation. So we're pretty much going to figure out how things diffuse through a medium. And heat through a metal rod is going to be the particular example. Before that, though, we need some preliminaries. There is something called Sturm-Liouville theory and the eigenvalue problem. Now, Sturm-Liouville theory, this is called SL theory. It's basically the study of differential equations, second order ODEs that are of this form. Now, that might seem very weird to you, but it should be clear, first of all, that you can expand this and write it out as a linear second order ODE. Just by doing the product rule of these terms here is going to give you a second order y double prime as well as a y prime. Then you're going to have expressions of y here. So it seems like a very weird way to rewrite a second order linear homogeneous ODE. However, one thing that's important is that any second order linear homogeneous ODE can be written in this form. This guy has its own integrating factor, and there's an entire theory, an entire corner of differential equations that studies second order ODEs in this particular form specifically. We're not going to go into that. We are going to study one specific scenario of this equation. This is when your P is 1, your Q is 0, and your W is 1. This means you can actually rewrite this equation in this form. And we are going to care about some specific initial conditions, y of 0 equals 0 and y of L equals 0. Now this problem is called the eigenvalue problem. Now why is it called the eigenvalue problem? Well, a lot of you are currently in linear algebra. a lot of you have taken linear algebra. So whether you're in 392 or 346, this should be familiar to you. Something like a matrix A times a vector X equals lambda X, right? Which I can bring to one side and write it in this form. This was called an eigenvalue problem, right? You can find the eigenvalues and eigenvectors solution of that matrix. And so you'll realize that this guy kind of has that same form to it. The differential operator can be thought of as a linear transformation, which can be represented as a matrix. We already saw that solutions to ODEs can be thought of as vectors in a vector space. And so basically, there is a matrix way of writing this equation down. And solving this equation is equivalent to solving this equation. And so it's kind of a matter of finding eigenvalues or eigenvectors, this is a generalization of the linear algebra problem, which is a very important problem to solve, by the way, right? So that's where the name comes from. In fact, solutions to this ODE, we call them eigenfunctions. Again, it's just a homage to the fact that we're thinking of them as eigenvectors. And the lambda solutions, the constant lambdas that make it work, we call those guys eigenvalues. Now, I'm not going to fully justify you. Surely you've seen it in linear algebra that it's important for various reasons. But in general, it's more important in general. It's very important to be able to solve eigenvalue problems whenever they show up. Here's a fun fact. Google is Google because of this reason. Why the Google search engine took over the scene and Google is now synonymous with search is because pretty much someone thought of the internet as literally as a World Wide Web, just some interconnected nodes on some network. And they imagined the idea of relevant search as being an eigenvalue problem. It turns out that you can reduce the problem of navigating someone to a relevant website as an eigenvalue problem. And a lot of other search engines at the time, there were tons of them. You know, I'm not talking about Bing, which is another one now, but back when I was a little Jhevon, we had like Webcrawler and Ask Jeeves and Lycos and all this other stuff, and everyone had their own favorite search engine. Now it's almost like everyone uses Google. Why was that? All these search engines were using like this dictionary lookup version to find a website, which wasn't very relevant. The website you were searching on was probably on page 59, and you know it was taking forever. But it turns out to envision it as an eigenvalue problem with Markov chains got us to the Google search engine. Now, of course, these days, the Google search engine also has a lot to do with ad revenue, so it's not exactly structured the same, but the birth of Google was due to the solution of an eigenvalue problem. So, you know, those situations where kids are like, you know what, I'm never going to use this in my life, you know? Yeah, Larry Page, Sergey Brin, when they were thinking of this problem, they're like, hey, you remember that thing we learned in linear algebra class? I think we could use that. And yeah, so eigenvalue problems, very important to solve in general, and we are going to learn how to solve this now. Now, it's not going to be anything crazy. As you can see, it's a second order linear ODE, constant coefficients. It should be a cakewalk. So let's actually go into solving this guy. So the ODE is ODE1. The set of initial conditions, I call that list 2. The combination of these two, I call that equation 3. So let's find the solution to 3. And the goal is, clearly y equals 0 is going to be a solution, not interesting. So we are going to want to find non-trivial solutions. So keep that in mind as we go through this. Y equals 0 is a solution, but it's not the solution we're interested in. So anytime we get a solution of y equals 0, we're pretty much going to ignore it and move on. We already know it's a solution. So there are 3 important cases to consider. Lambda is less than 0, lambda is equal to 0, and lambda is greater than 0. You'll realize that this equation breaks into 3 different cases based on those values. So let's actually go through case 1. Lambda is less than 0. Okay, so let's imagine that our lambda is less than 0. So we have our y double prime plus lambda y equals 0. And you guys tell me, how would I solve this? So lambda is a negative number. How would I solve this? Quick review from the beginning of semester. What do? Lambda is a constant. Maybe someone just chime in and tell me what to do. You don't have to like type out the exact answer. That's not what I'm asking for. Just tell me what we do. Yes, it's a linear second order. How do we solve it? What do you do? Characteristic equation. Right. So what do we get? What is the characteristic equation? So it's actually going to be r squared plus lambda equals 0, which means our r squared is equal to minus lambda. Now remember, your lambda is negative, so this is a positive number. So this means your r is going to be plus or minus radical minus lambda, which is going to be a real number, right? So it looks weird because there's a negative under a radical, but remember, your lambda is negative, so this is actually a real number solution. Then what's going to happen? Your y should look like c1 e to the minus lambda t plus c2 e to the minus radical minus lambda t, right? Now we have initial conditions to satisfy. Y of 0 equals 0 would mean that c1 plus c2 equals 0. Right? So that would mean that your C1 is minus C2. Now y of L equals 0 is the other initial condition that we care about. And later on, you're going to see why we care about this initial condition, which means if I plug in C1 e to the radical minus lambda L plus C2 e to the minus radical minus lambda L, set that equal to 0. And on top of that, I am going to plug in C2 equals negative C1. So this means you get C1 times e to the minus, right? So this guy I can think of as minus C1. And so I can factor out a common term C1, and I would get this guy. Now, this is only 0 if your L is 0, but in general, this is not going to have a nice solution. And we are going to want L to not be 0. So tacit assumption, L is not 0 here, because of course, we already have what's going on at 0. So we're thinking L is different from 0, which means that this is never 0. And so that would imply that C1 equals 0, which also implies that C2 equals 0, which implies that y equals 0 is the general solution here. However, again, that's a trivial solution. We don't care. So that is case 1. So if your lambda is negative, we only get the trivial solution, not interested. So we go over, what if our lambda is 0? So that would mean we have y double prime plus 0y equals 0. Well, that just means y double prime equals 0. How would we solve that? Well, you integrate once, you get a constant, and you integrate again, you get that. Now you know that y of 0 equals 0. This means that your C2 equals 0, and then you get y of L equals 0. This would mean that 0 is equal to C1L plus 0. And your L is not 0, so this gives you that C1 equals 0. So again, we get y is 0 is the general solution. But again, this is the trivial solution. We don't care. All right, so one case left, and hopefully this one gives us something that's usable. So we go to the last case. Lambda is positive. So we're using y double prime plus lambda y equals 0. Lambda is positive. This means, again, you go by the characteristic equation. And so your r squared would equal to negative lambda. And so your r would be plus or minus radical lambda. Now this guy is complex. In fact, this would look like plus or minus radical lambda I. So we have complex solutions. This means our solution looks like C1 cosine lambda t plus C2 sine lambda t. Right? And so now we have to check our initial conditions. Well, y of 0 equals 0. Well, this would mean if I plug in 0, cosine of 0 is 1, sine of 0 is 0, so we just get 0 equals C1. All right? What about y of L equals 0? Plug this in. I already know that C1 is 0, so there's only the sine part to care about. So this would mean that 0 is going to be equal to C2 sine of lambda times L. All right, now, L is not necessarily 0, which means that the sine is not necessarily 0. So remember, we don't want C2 equals 0. This means we have to assume that our sine function is what gives us the 0. Okay, now, if sine of radical lambda L gives us 0, what does that mean the angle is? Zero is only one solution. Yes, it's one of them, but I don't want the trivial solution, right? So give me some other numbers. Also pi, yeah? Are we gonna individually list all of them? Because there are infinitely many. N pi, right. It's equal to n pi, where n is any integer. Right? The sine of x is 0 when x equals any integer multiple of pi, which in fact means that my radical lambda looks like n pi over L. Now, this means my solution looks like, where is it? It's C2 sine of radical lambda, which is n pi over L times t. Or to be a little bit more suggestive, or if we had the independent variable x, this would look like y equals C2 sine n pi x over L. Right, well, it's not a sine series, but it's kind of reminding you of something, right? It is reminding you of something that we talked about yesterday. It's very interesting that that angle, that particular kind of angle, n pi x over L would show up here. But let's actually continue. But that actually gives us the solutions. So this here is what we would take as the eigenfunctions. And this means they have some corresponding eigenvalues. The corresponding eigenvalues are, well, our lambda, our radical lambda was this, so our lambda can be thought of as n squared pi squared over L squared. So these guys are the eigenvalues, and the constant times that sine function happens to be the eigenfunctions. So a non-trivial way to solve this system that I just mentioned here is with this particular solution. Now remember that. In fact, like take a picture or something. So this is the above solves y double prime plus lambda y equals 0 with y of 0 equals 0 and y of L equals 0 in a non-trivial, very nice kind of way. All right, so you can take a picture of that. We're actually going to use that later. It is preliminaries for a reason. We're going to need to know these facts. 5, 4, 3, 2, 1. Okay, take a picture of that. Now I don't think, yeah, so here, oh, it's actually written nicer here. I forgot that I actually typed this up for you guys. If you've ever had trouble reading my bad handwriting, you can take a picture of that. So this is the summary of what we've just discovered. The solution to this equation with initial conditions that is given by that. The eigenfunctions, and I'm ignoring the arbitrary concept of integration here, it's fine. And so that is going to be sine of n pi x over L. And the eigenvalues are given by lambda equal n squared pi squared over L squared. All right, cool. Again, isn't crazy. This is a regular second order ODE. We're kind of used to that. And it shouldn't be too much trouble to have solved that. Let's move on. So this is the preliminaries. We need to know this for what we're going to do. We're going to be able to use this fact at an opportune moment. Now, let's get to the main application of the day, the main star of today's lecture, the heat equation. We're going to talk about the derivation of this equation and the solution to it. Now, in the beginning, it's going to seem like it's very complicated, but it turns out, given all the facts that we've studied over this entire course, putting these guys together in a very creative way, we're going to actually come up with a very simple way to solve this equation. It's going to take almost no calculations. Once I actually do the derivation for you, it's going to be more of a, I can solve this by looking at it kind of situation, which is very surprising. Like when someone actually describes the problem to you, it might sound like it's a very complicated thing to solve, but we're going to figure it out. Now, this is, the heat equation is referring to a PDE, which is like an ODE, but instead of ordinary derivatives, there are partial derivatives. So I shortly spoke about this in the beginning of the course. I mentioned that PDEs is when your dependent variable actually has several independent variables. So it's not just a y of t, it's a y of t1 comma t2, or a y of x1 comma x2 comma x3 comma x4. All the way up to xn. You can have n independent variables in general, right? So now when you're taking a derivative, you have to take partial derivatives. You have to know derivative with respect to who. So now when you end up in that situation, you say you're solving a partial differential equation. Now, partial differential equations, super important, highly applicable, very important area of applied math is PDEs. It's a little bit more esoteric, so not a lot of people think of it. When people think applied math, they tend to think probability and statistics. However, the area of applied math that PDEs covers is just as large. It's just that the applications of it is usually very sophisticated that most people never even think of it, right? So very big thing in applied math. You can't be an applied mathematician without knowing a lot about PDEs. So PDEs are very important. Now, when it comes to PDEs, you go into a first semester course of PDE, which at City College, I think we have an undergrad course now, but traditionally we've only had a graduate course. The first semester of that graduate course, you would study 3 fundamental examples of PDEs. These are like they don't cover all possible cases of PDEs, of course, but they're very basic fundamental examples that you can apply. So this is like me teaching you what a first order linear is and what a second order linear is. Not because all equations are like that, but when you get the lessons that you can learn from solving those guys, you can apply them to bigger things. So just like how we used the solution to an Euler equation to figure out how to find series solution to singular point, to general nonlinear ODEs at singular points, same kind of idea. So the fundamental examples are 1, the wave equation. So this is like if you're into fluid dynamics, You are some sort of engineer, you're dealing with fluids, dealing with water flow, fluid flow, air flow, any of that stuff. If you study that at a high level, you are going to be very good friends with the wave equation, right? Not the wave equation from physics. It's actually a different wave equation, right? So it is pretty much an equation of this form. I have my u, which is my dependent variable of two independent variables, t, which represents time, and x, which represents location, right? And it's saying that the second derivative with respect to time is equal to some constant times the second derivative of the function with respect to position, right? This describes the propagation of waves. It does water waves, sound waves, a lot of things, right? Big hitters like D'Alembert, Euler, Bernoulli, which I now have to specify Daniel because the Bernoulli was a powerhouse in mathematics. Like there are so many mathematicians from the Bernoulli family, you have to kind of specify which one you're talking about. And Lagrange, they all studied the wave equation. They made great breakthroughs in this equation. If you study the wave equation, you will be studying the work of these giants here. Laplace equation. This was studied by Laplace when he was studying gravitation. It has to do with the deformation of bodies. And it turns out you can consider gravity as sort of a deformation of space-time. So you want to study gravity, it turns out, you're right, you're going to the general theory of relativity or anything of that such form. At some point, you're going to talk about the Laplacian. At some point, you're going to need to deal with and grapple with the Laplace equation, right? So this is a PDE that talks about the deformation of bodies. You take a flat metal sheet, you start to bend it and twist it, find a function that goes to and measures the slope at any point over that twisted form, and the Laplacian is going to show up. Very important and fundamental example of a PDE. Finally, there's the heat equation. This is also called the diffusion equation, as I mentioned. This is the one-dimensional version of the heat equation. You can have a multi-dimensional version of it. And basically, the heat equation talks about how something diffuses through a medium. So it could be heat diffusing through metal. It could be toxic air diffusing through a room filled with fresh air. It could be anything of that sort. It could be dye diffusing through a puddle, whatever, right? Whenever you have something kind of diffusing through a medium, this PDE is going to be there some way, somehow. It was studied by our old friend Fourier, right? So the same guy who invented the Fourier series, he did a lot of work in the heat equation. Remember, Fourier was also a physicist. So he did a lot of things with conduction, heat conduction. He actually invented his own law of conduction called the Fourier Conduction Law. It's actually pretty analogous to a basic law of thermodynamics, which we'll talk about in a little bit. This is the guy that we're going to focus on, the heat equation. Right, so these other two very fundamental examples, very important. You would study them in a typical PDE course. You're also, depending on what section of engineering some of you are in, or you will see this in your engineering classes as well as if some of you are physicists, chances are you'll see these as well. You'll definitely see the wave equation in physics. But yeah, and you'll see the Laplacian all over the place actually. But our focus will be on the heat equation. Okay, so that's what we're going to do. In particular, we're going to focus on the one-dimensional heat equation. And there are very technical derivations of this. We are going to actually derive the heat equation. I'm going to tell you where this equation actually comes from. How do we know that this is the equation that describes heat diffusing through a body? I'm going to come from a very intuitive perspective. So I'm not going to get all very calculations heavy and very like theoretical, even though a theoretical treatment of this would require a lot of knowledge in physics and engineering, which I'm just not going to assume that you all know. But I am going to pretty much kind of go with the treatment that comes from, you can actually check out some videos here. These are kind of the inspiration of why I decided to go through this angle as opposed to the angle that your textbook goes through or the angle that a typical physics textbook would go through. I really like how this guy spoke about it, and I'm pretty much going to give his view. I don't think it's his view specifically, but this is the first source in which I saw it kind of presented in this way. So that's a reference for you there. Probably you don't want to watch that video. It's a lecture series on PDEs. You probably don't want to consume that until after this class because you don't need to really know it. It's just if you're curious about more of this stuff, I would check those videos out as kind of to dip your toes in the water, so to speak. Okay, so here's the situation. Here's what we're going to deal with. This is the situation we care about. You have a metal rod. We're going to assume that it's insulated on both ends, so it's not losing any heat out of both ends, and the temperature at the ends are maintained at 0. The rod has length L, and basically the function that we care about is u of xt. So x is measuring the location along this rod that you are. If you imagine that it's placed on the x-axis, x is telling you the location and the position along the rod that you are. T represents time. And here's what we're going to think about. What if we started heating some point in this rod, and then heat started to diffuse throughout the rod? U of xt is going to measure what is the temperature at a certain point at position x and at time t. So for example, if the rod has length 10, so L equals 10, then U of 2 comma 3 would be what is the temperature at time 3 seconds at position 2, right? So that would be the function. That's the guy that we actually want to measure, right? That's the guy that we claim is governed by this situation. Okay, so we're going to want to solve that situation. How can I measure the distribution of temperature throughout this rod? Now, it's a very complicated question. How am I going to know how it's measured? We're going to start out by assuming certain ideal situations. So we're going to be physicists for a while, you know, assume the cow is this frictionless sphere so that we can get a problem to work out. So we're going to do that kind of thing for the moment. We're going to make some ideal assumptions that's going to help us get a handle on the situation. And it turns out, after we figured out the solution to this ideal situation, it turns out you can go back and empirically verify that all your assumptions actually pan out in the real world. And that's what we realized, they actually pan out in the real world. But just to get a mathematical model off the ground here, let's make some assumptions. So first, we're going to say that the rod is infinitesimally thin, which means it's a very thin metal rod. We can almost assume that's a one-dimensional object, right? Second assumption, if we take cross sections, at cross sections, which means if I slice this perpendicular to the x-axis and I just take that little disc, right? So if I just go in here and I slice a cross section, and I take it out and I have that disc, then we're assume the temperature is constant along this disc. Okay, we're also going to make the assumption that the rod is perfectly insulated, meaning we're going to assume that it's not losing any heat to the environment. It's not losing any heat through the left or the right or through the skin. So we're just going to assume that once I start heating this rod, the distribution of heat will flow through the rod itself and we won't lose any to the atmosphere or whatever, right? It's just going to spread out through the metal. We're also going to pretend, and this is a big assumption here, but there are going to be situations in which we can kind of measure it. We are going to pretend that initially we actually know what the initial temperature distribution is. So we might start with a situation where we know that the rod throughout has a constant temperature of 5 degrees, right? We start with a rod, we know it's 5 degrees. And then we're going to heat up a portion of it, right? Or maybe I know that, well, the middle portion is at 10 degrees, but over here it's at 3 degrees, and over here it's at 5 degrees, etc. We're going to pretend that initially we do know the temperature distribution. So at time equals 0, there we know some function f of x that is going to measure the heat at position x, right? So these are the assumptions. So under these assumptions, let's actually solve the heat equation. Are you guys still, I just want to double check that you guys are still hearing me. I got a message that says my internet connection might be unstable. Okay, all right, great. You're all with me. Okay, good. Uh, is this interesting to you so far? I don't know. Are you guys actually interested in actually finding the answer to this question? I think it's a real cool application. Anyway, it's going to tie together a lot of things that we've been doing. Um, so here's how it's going to look. So here is the rod. Blue can represent what the initial temperature was. It's a blue rod right here. But then I put a candle and I start heating it in the middle, right? So in the middle now is getting very, very hot, which is indicated by the red temperature. And it kind of diffuses throughout the rod, right? So the yellow is a little bit cooler, the green is a little bit cooler, the blue is cooler still, and it kind of diffuses like that, right? So pretty much I want a function u that is going to measure how hot is the blue part? How hot is the green part? How hot is the yellow part? How hot is the red part? I want to actually measure how this temperature is distributed after I do that. Now, at the endpoints, you see the assumption is at x equals 0, I'm assuming that at time equals 0, the temperature is 0 at x equals 0. At x equals L, the temperature is L. This shouldn't really be, this shouldn't be T, this should be temperature. I mean, I was going to put temperature for T, but I should have put uppercase T. So that's a typo that needs to be fixed. Yes, this would apply if you apply heat to an endpoint, it would just distribute the heat to the right. But we're assuming that no heat can be lost outside of the endpoint. So there's nothing being lost to the left of the rod. Everything is going to stay within the rod. But yes, I could heat it from the right side, and it would just you would have just red toward the left, and then it will just get progressively bluer as you move to the right. Yeah, I just put in the middle just because. It's going to give me more options to show you the concept that I'm going to want to illustrate later by heating it in the middle. But no, if you look at a lot of images from, if you just Google this from Google, if you look at a lot of images, they're heated from one endpoint and they show it, but I think it's going to be a little bit more instructive if I heat it in the middle. In this lecture series that I showed you here, he actually heated the rod in 2 different locations. He put a candle over here and a candle over here, which is again a very nice illustration, but it's not as simple as what I want to show. But then the other ones where they only heat from the endpoint is not as general as I'd want to show. So I just chose something right in the middle. So pun definitely intended right there, but putting the heat source right in the middle is going to give me the generality that I want to present. Okay, so I start heating up the middle. So it's getting very hot in the middle and heat is diffusing throughout the rod, right? All right, now, at this point, there should be a law of thermodynamics that pretty much everyone should know. I'm guessing everyone actually knows. Tell me, how do you expect the heat to flow? Like if I were to ask you, describe to me how you expect the heat is going to flow throughout this rod. How could you tell me about maybe the direction of heat flow or something like that? How would you describe it? Someone tells you, describe to me how heat flows. What would you say? High to low, yes. In other words, heat will move towards the colder temperature, right? There's a law of thermodynamics that says heat is what travels, cold does not travel. So even if you feel like, if you touch something, like if you hold an ice cube in your palm and you feel the cold, you might get the sensation that the cold is traveling to your hand, but that's not what's actually happened. It's the heat from your hand that is traveling to the ice cube, and that's why the ice cube melts. You are actually transferring heat from your hand to the ice cube. There's a law of thermodynamics that says heat flows from hotter areas to colder areas. Right? Now, Fourier come up with his own conceptualization of this. Of course, he made it sound a lot more mathy, but basically this was the assumption that was made. You know what? The cooler parts of the metal rod over time will start to heat up. There's going to come a time where your temperature, you can assume, is evenly distributed throughout the rod. But to get to that point, what's going to happen is the colder parts of the rod will eventually start to heat up. So the heat is going to spread out from the center. and it's going to start heating up the other areas of the rod. So that is what we end up we would imagine is going to happen. Now, here's what we're going to do. Let's actually graph the temperature distribution. So let's say we fix a point in time and we graph the temperature distribution. We expect it to look somewhat like a bell curve. In the middle, it's going to have the highest temperature, right? So here, highest temperature. And it goes up. Now, over time, we expect the endpoints to start getting hotter, so this curve is going to start rising up. Whereas the heat will transfer from the middle towards the end. So we expect the height of the bell curve to start decreasing and the endpoints of the bell curve to start increasing. So eventually it's going to kind of go towards a straight line. It's going to start morphing into more of a straight line. U is just the temperature, the temp distribution at some time Tn, right? So Tn after n seconds or whatever, right? So I'm thinking of a fixed time in my mind, okay? So at this time, look at the temperature distribution, right? So after 2 seconds, if I were to measure the temperature and plot a graph, this is what it's going to look like. I want to ignore time in my graphs because technically what you would have here is a 2D situation where x is being measured one way and t is being measured one way, and you would have like this hump, right? So it's a 3-dimensional hill, but I want to get a cross section here. I want to slice through at some t level, and I would get a trace here that when I map over there, I would get like a bell curve in the UT plane. So U is the vertical thing, and I'm looking in the the UX plane, okay? So that is what I would expect the initial temperature distribution to look like. Okay, now, what would happen over time? So let's say now, again, I'm still thinking of time being invisible. I'm still looking at the projection in the UX plane. However, I'm moving the T plane throughout this mountain and seeing what would I expect to see happen. Well, as we mentioned, based on what we mentioned above, this is what we expect. So here you see I don't put Tn. I'm thinking now T is changing. What would I expect to see? Well, for one, I expect the hottest parts, if I especially start to remove the heat source after a while, I expect the hottest part to cool down as it starts distributing heat towards the endpoints. I also expect the endpoints to start heating up, right? Now, this is overall the picture. Now, what can we expect to happen as I move throughout this curve? Well, if I move a little bit to the right, let's say I move a little bit to the right over here. What's going to happen is, again, this is still a hotter part of the rod. The heat source is over here, so it's hotter to the left than it is to the right, which means the heat is going to leave this point and move over. So this part is also going to have a decrease in temperature. However, it will have a smaller temperature decrease than the middle, right? The middle is at the highest temperature, so he's going to see the biggest drops. As we move away from that, the drop in temperature is going to get by magnitude smaller. Similarly, if I go over to the left side and start imagining, well, what would the temperature change look like as I move over time? Well, I would expect parts here to be heating up, but heating up by less and less. There will come a point, kind of like an equilibrium point, kind of in the middle, where you're just as hot to the left as you are to the right. And so these guys pretty much stays the same, but everywhere else beyond them will cool down to their level, and everyone else to the other side will heat up to their level. So if you're going to be at a point here, so eventually this green line is representing what the equilibrium is going to look like. Eventually the heat, if I just think of it as perfectly insulated, the heat is not escaping. Eventually what's going to happen is that the rod is going to hold all the heat, and it's going to be evenly distributed over time. As time goes off to infinity, I will have an even heat distribution, and it's represented by this like red line. But in the middle, if you're not at that line, you will eventually increase or decrease towards that line, depending on whether you're hotter or colder than that line. Graphically, what's happening is the graph is going to move towards that line somehow. Okay, so this is what we expected to happen over time. And this is what Fourier would realize would happen over time. So here's another ideal assumption. What Fourier decided to look at, and he was studying this, he decided to look at the concavity. Now here's something interesting that you would notice about the concavity of this graph. Notice what we are in the middle. So in the middle here, we are concave down, meaning the second derivative, if I look at uxx, it's negative. If I look on towards the tails though, it, undo. If I look towards the tails though, over here we're concave up. Another way of saying that is my uxx would be positive here. If I look over here, again, we're concave up, which means that uxx, the second derivative with respect to x, is positive. Now, here's the stroke of genius, right? The genius comes out sometimes out of the simplest kind of ideas, the simplest most novel conclusions. Here's something that you can notice. The sine of the second derivative is the same as the sine of the concavity. Notice that when this guy is positive, it is associated with a positive temperature change. Similarly here, negative. And what's happening in the middle when it's negative? The temperature is dropping. It has negative, and it's associated with a negative temperature change. So the temperature is falling in the middle, but it's rising at the ends. And this happens to coincide with the sign of the second derivative. Again, positive, and coincides with positive temperature change. So Fourier noticed this, and by the same token, he also made another assumption, which again, it's a mathematically ideal assumption. He had no way of knowing this in the beginning that this would be the case. But again, the length of my arrows here kind of describe to you what I'm thinking of the temperature change. You'll notice that when the concavity, and this is good, this is also tying into a lot of Calc 1, where we switch from concave up to concave down is an inflection point. What happens at the inflection point? Well, at the inflection point, our uxx is 0. Right, now we increase in magnitude going towards here, where it gets the most positive that it could be, and it decreases in magnitude going towards there, which means not only is the sign associated with the temperature change, but we also can assume, ideally, yes, but we can make the assumption that it is proportional, meaning the more positive the second derivative is, the greater the temperature change. The higher the magnitude of the second derivative, it could be positive or negative. The magnitude of the second derivative is proportional to how much the temperature is changing, right? The temperature change is almost 0 here. It happens to be the case that the second derivative would also be 0 there, and etc. You assume that as you move away from the equilibrium, that it's going to be associated with a proportional change. And so he made that assumption, right? So this is the idea. Here's what Fourier noticed. The sign of the concavity matches the sign of the temperature change, and it's pretty much proportional. The farther you are away from the equilibrium, the more your magnitude is going to change in terms of temperature, and at the same time, the greater the magnitude of your concavity. So that is to say, positive temperature change is associated with positive concavity, and the larger the temperature change, the larger the magnitude of concavity. This is basically saying what? The rate of change of temperature is proportional to the concavity with respect to x. That's this right here. If you were to write this in mathematical symbols, what would that be saying? It would be saying this: u sub t is equal to some constant times u sub xx, which, as you notice, is very close to the heat equation. But that's the ideal assumption that gets us on the road to the heat equation is that guy. Now, the constant of proportionality is always assumed to be positive because it will depend on the material of the rod. So it depends on all sorts of physical features of the rod. So it's always considered to be positive because it would be determined by density and special heat and things of that sort. So we always think of the K here as positive. So we mathematically just represent it by a square. Traditionally, we set K to be alpha squared. We just use the Greek letter alpha, and that leads us to here, and gasp, that's the heat equation. So that's where this equation came from. So I told you originally that this is the heat equation. Where did that guy come from? It came by reasoning like this. This was the intuitive reasoning, and you can kind of go back through experimentation, through theorems from physics and ideas from physics. You could actually derive this directly. And there are, I've seen YouTube videos where people actually derive this directly, but the knowledge of physics and math that you would need for that is beyond the scope of this class. So I'm not going to do it. So I'm just presenting the intuitive derivation. So that's how we get to this equation. By the way, alpha squared, like I said, you could go in and measure things with physics and get pretty accurate measurements on all of these guys. Alpha squared is known as the thermal diffusivity constant, and we actually know how to compute it. It is kappa over rho times S, where kappa is the thermal conductivity of the material, rho is the density of the material, and S is the specific heat of the material. So we can actually compute what this constant of proportionality would be. It's given by that ratio, in fact. But to figure that out, you'll need to know a lot of physics that we don't have time for. So yeah, and like I said, you can go back and you can empirically verify everything here. So we started out with some very ideal assumptions, but it turns out in the real world, this actually ends up being a very good model. Ultimately, we get the following. So if I put this equation together with my ideal assumptions about how it's insulated and about what I know about temperature and all that stuff, I get this sort of system here. So here's the PDE, that's the heat equation. Here are the assumptions. I'm assuming that at position 0 for all time, the temperature is 0. So it's perfectly insulated on the left. At position x equals L, at any time, the temperature is 0. So for all time, the endpoints have temperature 0. So that leads me to this line here. This here is called the initial conditions. So this here is referred to as the IC, initial conditions. And conditions. Then we have ux of 0. So this is at time 0. And I'm assuming that I know how to measure the temperature throughout the rod. So for x between 0 and L, I know at 0 and at L it's 0. But for all x values between 0 and L, my temperature is given by this function at time equals 0. I actually think this was the other way. This is the boundary conditions, and this is the initial conditions. So that's a typo here. So I mentioned the second line should be the third. And the second. I'll change that later. Let me put, just make a note of that typo. The diagram should say temperature, and I have to fix IC and BC. Okay, let's continue. Okay, now this guy here, whenever you have a PDE, you're given boundary conditions and initial conditions. You call that a boundary value problem, right? So this is analogous to finding an initial value problem for an ODE, right? So now you know the name of your textbook is Elementary Differential Equation and Boundary Value Problems. Now you know where the name Boundary Value Problem comes from. It comes from this guy, studying problems like this. It's studying PDEs where you're given conditions initially, as well as conditions on the boundary of the PDE. And for higher dimensions, your boundary doesn't have to be just coordinates or endpoints. They can be a curve, right? Or they can be literally a 2D surface or a 3D surface. Your boundary conditions can work in higher dimensions, but we're looking at the one-dimensional case here. So your boundary is actually a zero-dimensional object. It's just a point. At the point 0, t, this is the condition, and at the point L, t, this is the condition. So this is called a boundary value problem, right? So now let's actually solve this. So we have just derived the heat equation. We know the boundary conditions that we want to satisfy and the initial conditions that we want to satisfy. Now let's look at the solution to the heat equation. How can we solve such an equation? Well, in good old ODE fashion, what we're going to do is start with a guess. That's kind of the game we've been playing. like when it comes down to it, we've been doing this for a long time, and we have all these theorems that in the background help us to know that we'll be okay after doing this. You can start with a guess, but as long as you get to an answer which you can verify is a unique solution, then whatever, your guess pans out. Here's the guess that Fourier started with. Fourier assumed, for the sake of simplicity, as a matter of hope, let's hope that the solution can be written in this form. It is a function of x and t, but he assumed it was separable. Let's pretend that I can separate all the x's and t's, and I can write my function as a product of two functions where one function will depend only on x and the other function will depend only on t. Now again, there is no guarantee that this is going to work out, but hey, we're launching a prayer. We have differential equations to back us up. We have the existence and uniqueness theorem to back us up. Of course, you would need to know that for PDEs, which I didn't talk about, but we do have such theorems in PDEs as well. So we are confident that we can kind of guess something, hope it works out, and we'll know that it will work out in the end, right? So x represents position, little t represents time, big X is just a function of x that you can separate, big T is the function of time that you can separate, okay? And u of xt is representing the temperature distribution, or it's more specifically, the temperature at position x at time t, okay? All right, now what we would do is, I know the PDE I want to solve. So just like we would with ODEs, you assume a solution of a certain form, then you find all the derivatives and you plug them in. So that's what we're going to do. So we will now, let's find the derivatives. So if I look like that, this means that u sub t would mean, well, my big X would just be a constant, and then I would differentiate the t with respect to t. So I can call that a prime because right here, as far as I'm concerned, the x is a constant. But technically, yes, you should be looking like a partial. It's like x times partial t, whatever. Then if I take my ux, x, that basically means my t is a constant, so it's going to stay. And I'm just going to take the second derivative of the big X with respect to x. So I'm pretty much going to have that. So now I'm going to plug these into that PDE. And what would we get? So the PDE says u sub t equals alpha squared u sub x, x. So this would give us big X times t prime is equal to alpha squared big X double prime t. So we now get this sort of equation. All right, so now we get to this. It's a weird kind of differential equation. In fact, it's kind of like a mixture of two ODEs because the big X is a single variable function. So the derivative here, we can almost think of it as a single ordinary derivative. And same thing here. So what do we do? How do we solve this? Well, we perform separation of variables. we go and we apply separation of variables on steroids. Essentially what we're going to do, separate the x's and t's. That's the idea. So I'm going to, let's say I put the t's on the left side. And let me move the alpha over here because it's going to look nice for something I want to derive later. And the x is on the right side. So now the t's and the x's are separated. So we can perform separation of variables for PDEs. At least if you think of them as separable. All right, now here is another very important thing, which initially you probably would never have guessed this, but hopefully in hindsight it would make sense. The only way for the above equation to hold is that if each side is a constant, right? Now it must be the case that these guys here must be equal to a constant. Now you might say, well, why would I make that assumption? Well, pretend it's not a constant. What would that mean? That means that this this equation here there's an expression with little t's over here, and there's an expression with little x's over here, which means that if this is not a constant, I would have found an equation that actually connects little t to little x in a relationship. But what would this mean? This would mean, for example, that time is dependent on the position that you're looking at. That doesn't make any sense. Time should be independent of your position, right? Time doesn't move just because I looked at a different point in the rod. No, time is moving regardless, right? My little x and my little t have to be independent, which means if they're not independent, if this thing is a constant, then this gives me an equation that I can define time in terms of x, which does not make sense. Time does its own thing. And so we have to assume that this is constant, because to assume it's non-constant is going to actually lead to a contradiction. We now have a situation where as long as I'm looking at a certain position, time, yes, big T is temperature, but big T is a function of little t. Right? So it's going to be like, it could be whatever, sine of big T, it could be like sine of, it could be sine of little t over t, and I call that big T or whatever. So big T is actually a function of little t. So every expression with big T in it is actually an expression with little t. And little t in our situation represents time. So there's no way for this to not be a constant. So by assuming that we can write it separable and separate the equations, we end up with, we're forced to assume that this equation is equal to a constant. So this means, this gives us the following. So for traditional reasons, we will set the constant equal to negative lambda. Why did I put a negative there? Just to make it look aesthetically pleasing and to kind of match up with something that we were talking to earlier. So that's literally the only reason, just for aesthetics. Okay, which means my x double prime over x is minus lambda. My t prime over t times 1 over alpha squared, that is negative lambda as well. They both have to be constant. However, whatever x and t are doing, when I put them in these ratios, they have to be the same constant. Otherwise, time is dependent on position, and that makes no sense. The universe doesn't make sense. Physics breaks down. We're at the singularity. Division by zero now works. All the bad stuff that you don't want to happen will happen. They'll make like there's a future where there's going to be a 25th version of the Fast and the Furious. You're like, what? They made 25 of these? Okay. So this must be the true. So this leads to a system of ODEs, which we need to solve simultaneously, like this one. So this leads to this guy, right? So here I just multiplied by x and I brought it to that side, and I get the top ODE. If I, again, multiply by alpha squared t, I get the second ODE. Now, I know about the initial temperature. T of 0 is f of x. So that I know the initial condition for that. There's one initial condition for this one. There are two initial conditions for this one. I know that x of 0 should be 0 and x of L should be 0. Right? Because that will give me the temperature at the endpoints. So I now have this guy. So let's look at these one at a time. I need to find a solution that works in both of these at the same time. What do you notice about the first equation? Notice anything about the first equation? It's linear, but let's get more specific. I mean, I wrote a lambda for a very particular reason, which we knew about linear equations for a long time. The thing I want you to notice is something that I spoke about literally at the beginning of this class, this lecture. It's a second order eigenvalue problem. That is the guy that we looked at in the preliminaries. It's this kind of problem. Instead of my y, I just have big X, but that's the kind of problem. And look at the initial conditions. It's the same initial conditions. This is why it was very important for us to be able to solve the problem that I solved in the beginning of class, because I know there was going to come a point where we need to be able to solve this ODE. So that's the first thing that we notice. The first equation is an eigenvalue problem. We know how to solve this. In fact, we already have the solutions. I copied it here for your convenience. So I'm not going to discuss that anymore. Right? That one would take us on a detour that's long enough for you to get lost in what I'm talking about. So I decided to take care of it in the beginning of class. So now you know those are the answers. The big X must be a sine function. In fact, sine n pi x over L. And my lambda must have this form in order to solve that. So I can even know what this constant should be, in fact. It's going to be minus n squared pi squared over L squared for each integer n. Now let's focus on equation 2. Now equation 2, that's literally a first order separable ODE. Divide by t, separate the variables, integrate both sides. You'll get ln of big T on the left, ln of absolute value big T. You'll get minus alpha squared lambda squared dt on the right. Integrate both sides. You're going to solve for big T. You're going to get the exponential. So that you should almost be able to do in your head at this point. And so we would get this. Now, of course, your big C is just the arbitrary constant of integration. We also know what lambda is. So lambda is the guy from here. So I'm going to plug that guy in. And we get this guy. So my big T must behave like this. It's e to the minus alpha squared times n squared pi squared over L squared times t. And so that gives us our general solution. Our general solution now looks like this guy. All right, now we're getting somewhere. So now we're here. All right, that's our general solution. Now, here's another thing that you can't forget. N seems to introduce a whole other variable. See, this guy can be solved for any integer n, which means now my solution here is not just one solution. It's actually a family of solutions. I can have a solution like this for every n value. That leads us to the following. Right? We have a solution, as you can see me highlighting here, we have a solution for each value of n, which means I don't have one solution here. I actually have tons of solutions. In fact, there are infinitely many solutions to this PDE. Like this, I can have I can measure, each of them is going to have its own constant associated with it. And so really what I have is a whole family of solutions, each with a potentially different arbitrary constant in front of them. So the general solution should look more like this, right? Now here, I'm setting my n equals 1, 2, 3 for the following reasons. First of all, n equals 0 gives me sine of 0, which makes this whole thing 0, which is a trivial solution. On one hand, I don't care. On the other hand, if I had to definitely get the trivial solution, I could just make my arbitrary constant here equal 0, and I can get it that way. So let's just ignore the n equals 0 part. Secondly, when my n is negative, what would happen is sine of minus x is equal to negative of sine x, because sine is an odd function. So I'd just be able to factor out a negative and absorb it into this constant anyway. So I can ignore all the negative n's. I can ignore n equals 0 because I can recover it from the cn's themselves, and it just makes it extra. It's superfluous to have them. So let's not actually talk about it. By the way, this is where the idea of a Laurent series comes from. When someone wants to not ignore these guys and also count the negative integers, now you have a series going down to negative infinity as well as going up to positive infinity. For us, we're going to start it at 1 and go off to infinity. So I have an infinite number of solutions here, and they can all be represented by this form. So we're getting somewhere. However, again, to tie in something that we learned a long, long time ago, the sum of any two solutions of an ODE is itself a solution. This is called the superposition principle, which means if I start adding up all of these different guys, add up the solution for C1, the solution for C2, the solution for C3, the solution for C4, going off to forever. If I add up all of those guys, I get another solution. So it's only befitting that the general solution is, well, it's a sum of all the solutions. It is, in fact, because there's an infinite number of these guys, the general solution is now an infinite series. So it turns out here that we have a series solution to the PDE. The general solution to this PDE is actually a series solution. Who would have thought it? Okay, so now we're at this point. Remember, I think of my u as it was the x times the t. The x gave me the sine part, the t gave me the exponential part, and this was the arbitrary constant. There has to be one constant for each n, so I have a bunch of guys like this. Summing all solutions gives me another solution, so the general solution looks like this. Whew. Okay, so we're actually getting somewhere. We're building up to the solution. Okay, awesome. Things are looking great so far. However, we also know a lesson that we've learned is a series is only as good as its coefficients. Meaning, if you can't tell me how to find the coefficients, you telling me a series solution is meaningless. What do I care? It's gibberish to me unless you tell me how to find the constants. So now we're in a situation where we need to somehow to be able to determine what the Cn are. Now, to determine the Cn, so that's what I'm mentioning here. To determine the Cn, we are going to get, let's put him here. We need to find the Cn's. Okay. Now, you might want to be worried now, well, how the heck are we going to find the Cn's? Well, to remind you, there is a piece of information we have not yet used. So if I go back to the initial statement of the problem, what in here was not used so far? What did we not apply? And another hint is, well, the Cn's really are the arbitrary constants of integration. So yeah, the third line, the initial conditions. If you want to find the arbitrary constants, you always go to the initial conditions. This is, again, a lesson that we've learned a long time ago, tying back in here. What we haven't used so far is the third line. Okay, so let me go to my solution and apply the third line. What would that mean? I'm going to go here and I'm going to plug in 0 for t, which means I get a 0 in the power of the exponential, which means the whole exponential term is going to visually disappear. It's just going to become 1. So that term is going to disappear. I'm going to get 0 here, and that whole thing is supposed to be equal to f of x, because the assumption is u of x0 is f of x, which means when I plug in that initial condition, I end up with this expression here. All right. Now, what do you notice here? Does that remind you of anything? This guy right here. You see something like that, what do you think? What does it evoke? What do you think about? It should evoke something because it's going to be on your test. What it evokes is on your test. What it should evoke. Bn for n odd, where are you getting that from? The name of the thing that you're thinking about that has a Bn in it. It's a sine series. It is the Fourier sine series. It turns out that my initial condition can be envisioned as the Fourier sine series representation of the function f of x. Wow, that is amazing. Gasp. And yeah, so in fact, I do know exactly how to find the CNs because I know how to find the solution, the coefficients for a Fourier sine series. So my coefficients are given by that. So at this point, you're like, I don't know. I don't know what that's supposed to be. Never mind. I have to work on my like funny sketches. So I do know how to find the coefficients. And that, of course, leads us ultimately to our solution to this whole problem. So what we wanted to derive so far is this guy. So this is what Fourier came up with, and this is pretty much how he came up with it. The heat equation boundary value problem and its solutions. The heat diffused through a rod, when we assume that the ends are insulated and that it's not losing anything to the atmosphere, and that we know the initial temperature distribution, can be expressed as this kind of problem. The solution to that kind of problem is a series solution, specifically this series solution. That is the function that will give us the temperature distribution at position x and at time t. And since it's a series solution, we want to know what the coefficients are, but no worries. It actually can be derived via the Fourier sine series coefficients. So a problem of this type will have this solution, and that is how you find the coefficients. That's the summary. Right. Okay, awesome. So now, took us a while to get here, but we're finally here. So we have maybe about 20 minutes left out of our time slot. So let's actually do some examples. It turns out though, once you know this, the examples are actually not going to be so bad. I just wanted to show you. So let's make the assumption that there's someone in the class. I'm not saying there is anyone, but anybody in the class who you don't care about any of this thing. You weren't interested at all. You don't care about the derivation and whatever, or how someone would figure out how to solve a problem. And I don't know, that's your prerogative. But if you're such a person and you wanted to know, out of everything that Jhevon was rambling about, what do I really need to know to be able to solve problems on an exam? Now, of course, it's multiple choice, so you should know some of the concepts in which I remembered to a light degree. But what is definitely inexcusable that you must know is this box right here. You need to have this box memorized. So probably you also want to like take a picture of this. Let me zoom out a little bit. So I'll give you guys 5 seconds to take a picture of it. That's what you need to know. The need to know of everything that I've been saying. So the concepts will be important later on in your classes, at least if it's in a math class, probably not so much in a physics or engineering class. They'll probably just tell you this answer and not tell you why, but whatever. Take a picture of that. 5, 4, 3, 2, 1. So that's the heat equation, and that's how we solve it. Now let's jump to some examples. Let's do some examples from the past finals. And you're going to realize that once you actually know this, the things that we have to do from today aren't going to be that bad. So here, this is a repeat of something that I mentioned is, hold on. So we actually did part A yesterday. So remember I told you the fall 2011 final problem 10 part A is what we did, where it asked us to find a sine series for a function. That is part A. Right? So we actually did that yesterday. It involved integration by parts. Well, we did the tabular method. It was here, right? So example 4 from yesterday's class. It's actually part A of the problem that we're currently looking at. Okay? Now we actually went through and we solved this guy. So we actually solved part A and we got the answer. The answer was the following. In fact, the part of the answer that we care about is this part, the Bn. Is this thing freezing now? Too much information, too much math is going on here. Did it actually copy now? I'm concerned. Okay, it did copy. All right. So, okay. So in a final, here's a problem that you could be seeing, right? So on your departmental final, maybe on the bonus problem, you could have a problem something like this. Part A, find the sine series for this function. Part B, use your answer in A to obtain a series solution u of t comma x for the partial differential equation, blah. Here you will notice that they gave us a boundary value problem, much like what I was describing to you earlier. Here it's like your alpha squared equals 9. So you see a problem like this. Your first step is to actually go through and find the Fourier series coefficient, the Fourier sine series coefficient, which we did yesterday. We did this yesterday. We actually knew what the Fourier sine series was. It looked like this guy. Which means that f as a series looked like was n odd 8 over n cubed pi cubed sine of n pi x. I believe our L is 1. Yes. Okay, so that was that. Okay, now we go on to B. So part B is the heat equation. This big monstrous PDE that strikes fears in the hearts of everybody. However, when you look at that and you read it, you would realize that what is described to you is what is in this box. So you literally need no calculations. You know that the answer to this is just this, where the Cn is that. So here we can just be like, we know u of, they said tx here, but xt is the same thing, is equal to the series n goes from 1 to infinity of Cn e to the minus n squared pi squared alpha squared t over L squared sine of n pi x over L, where our Cn equals Bn above, and L equals 1, alpha squared equals 9. And I literally go now and plug those guys in. Now the series only works on odd n, so I'm going to put n odd here. And then my Cn is going to be 8 over n cubed pi cubed e to the minus alpha squared is 9, so it's 9n squared pi squared t over L squared, which is 1 sine of n pi x. That's the answer. That's the solution to the heat equation. And voila, we are done. We now know how to do the very last problem in the syllabus of this class. And it was very long-winded to explain how we got to this point, but I think it was a very cool derivation. I think the thought process was interesting, which is why I really wanted to like go through it with you guys. But at the end of the day, this is all you need to know. If you see a problem looks like this, the solution looks like this, where the coefficients come from the Fourier sine series coefficient. Like, worst case scenario, if you get nothing from this class, you need to get that. If something looks like this, the solution looks like this, where the Cn is given by the Fourier sine series coefficient. That's the summary. However, I really wanted to show us how we even got here. How we can go from seeing a problem in the real world, mathematically creating a model, figuring out that model is a PDE, developing the PDE, and then solving the PDE, right? So if you're an applied mathematician or a physicist, or you're an engineer that can do more than just blindly plug things into a calculator and can actually solve a problem when they see it in the real world, this is the kind of things that you're going to be able to do. Of course, it's going to be, in today's world, it's going to be a lot more complicated. But you're going to see something in the real world. You're going to try to come up with a way to describe it mathematically. Very, very often, especially in engineering and physics, a PDE is how it's going to be described. Very often. It's going to be very, very often that that's going to be the case. Then you're going to have to somehow figure out a way to solve that PDE. Now, there are some classes of PDEs that we know very well how to solve, but to solve others, you need to take a PDE, you need to take a class in PDEs. So eventually, we now get here. Now, what I want to do for the remaining minutes is to actually solve a problem from scratch. As we now know, part B is going to take almost no time. The real work happens in part A, where we're asked to find the Fourier sine series. So on one hand, it's good because it's going to be a review of what we did yesterday to make sure that we know that and we're ready for the test tomorrow. And on the other hand, it's also covering a topic. So it was very nice. We used everything that we learned from the beginning of the class right to the end of the class up to yesterday to bear down on this physical phenomena. And we nailed it, and that's the solution. Let's actually do a problem from scratch. So this is from the spring 2011 final, also problem 10. Obviously that year, the same person wrote the final and they used the same format. The formats between the two were very similar. Problem 10 in both of these exams is a problem like this. They ask you about the sine series specifically, and then you pretty much use your answer to solve the part B. So let's actually look at this. F of x equals 1 on 0 to pi. Of course, that means your L is pi in this scenario. So you kind of have, that's your function. And you want to extend it as an odd function. So you want to do this. So here you get like it's actually a model of what we call a square wave, lots of applications there in signal processing, etc. Right? And that's going on forever. We want to find the Fourier sine series for this guy. Well, how did we do it? Well, we have to find the Fourier sine series coefficients. So we need to find the bn's. The bn is going to be given by 2 over L, integral from 0 to L, of f of x times sine of n pi x over L. L is pi, so this is going to be 2 over pi, integral from 0 to pi, of 1 times sine of nx, right? Because L is pi, so the pi's cancel. This is going to be equal to, well, the integral of sine is minus 1 over n cosine nx. Between 0 and pi. So this is going to become minus 2 over n pi cosine n pi plus 2 over n pi. In other words, this is going to be minus 2 over n pi times minus 1 to the n plus 2 over n pi. What you will notice, this is going to give you two things. When your n is even, you would get 0. When your n is odd, you would get positive 2 over n pi plus 2 over n pi. You would get 4 over n pi. So that means your Fourier series of x is equal to, well, the series summing over odd n of 4 over n pi times sine of nx. Yes, because L is pi. Or another way you can write this, if you want to account for everybody, just do something like n equals 0 to infinity of 4 over 2n plus 1 pi sine of 2n plus 1 x. So that would be the answer. All right, now we move on to part B. Now, if we look at part B, you will notice, again, it looks like a very familiar form. It is actually a boundary value problem. We have the boundary conditions and the initial conditions. So here I can see that my alpha squared is 64. So here I will notice that this is a heat equation boundary value problem with alpha squared equals 64 and L equals pi. Right, if you go up here, it also says L equals pi. L would be the guy that's over here, the left endpoint for x, and x goes between 0 and pi. Remember, x goes between 0 and L. So this falls very nicely into the thing that I described earlier, which means u of xt equals the series Cn e to the minus n squared pi squared alpha squared t over L squared times sine of n pi x over L, where Cn equals Bn from part A. L equals pi, alpha squared equals 64. This would mean that my u of xt equals, just caring about the odd integers, 4 over n pi, if memory serves. Yeah. E to the minus 64 n squared t, because my L is pi, so L squared is pi squared, it cancels the pi squared. And then I have sine of nx, because again, L is pi, so the pi's cancel. And that's the answer to part B. So that would be what a full problem would look like, a problem of this type. It's also possible that you would have been asked in part A to find the full Fourier series, in which you have to compute the ANs and the BNs, but you would know that for the part B, you ignore the A coefficient and you take the BN coefficient as your answer for part B. And so we end up here. Yeah, and that's it, guys. So I would say don't practice the corresponding problem from the fall 2017 final until you're actually practicing for the final. In the meantime, you'll have more practice examples from your homework as well as the suggested problems from your text. And that being said, that's it, guys. That's all she wrote. That's the entire course. That is Math 391. We've covered everything just in the nick of time. Covered the last material on the last day. I had a lot of fun explaining it. Hopefully you guys had a lot of fun listening and in participating whenever you did. But yeah, that is basically all she wrote. As well as email about the test tomorrow. I mean, I might send out an email anyway, just reminding you guys of the time, but it's everything since test 1 up to yesterday. So it's everything from test 1 all the way up to Fourier series. What we did today would be bonus. No, the final is on July 23rd. This is literally in the syllabus as well. So this is, the final is on July 23rd. I believe it's from 5 to 7:15 p.m. So Thursday, July 23rd is the final. So the final is 1 week from today. That is going to be on Blackboard. I got no information about that as of yet. If over the weekend I find out anything about the final in terms of what's the format, how many problems you have to do and any of that, I will also let you guys know, but it's on the 23rd. From 5 to 7:15 is the final. Our last test, the second test, is tomorrow between the window of 12 to 3. The test itself is about an hour and a half, and you'll have some time to actually upload scans, but you have to take it within the window 12 to 3. And then that covers everything since test 1 all the way up to Fourier series. So it starts around higher order ODEs. So it will cover higher order ODEs, series solutions at ordinary singular points, Euler solutions, Fourier series. Yeah, everything since test 1. Test 1, I think, went all the way up to second order linear ODEs with constant coefficients and some applications, like the spring problems and that and tank problems and that sort of stuff. Everything after that we covered, the existence and uniqueness theorem, higher order ODEs, It's going to be on grade scope again. So the test is going to be on grade scope, just like last time. The final is on Blackboard, as far as I know. The last information I got, the final is on Blackboard. And last semester in the spring, I don't know if, again, I have no information. Literally the fall semester starts in like a month, and I don't know what or if I'm even teaching in the fall, because the department hasn't given any information. Like they do everything very last minute. So I don't have this information, but judging from what happened in the spring when we gave the final online, it was on Blackboard. I believe the differential equations final had around 13, 14 problems. You had 2 hours and 15 minutes. And you couldn't move forward or backwards through the problem. So like how you see on my test where you can read through all the problems at the same time, you can't do that with this. You have to do problem 1, make sure you get it right, and then you move on. Once you move on, you cannot go back. So make sure you get it right. Then you look at problem 2. You cannot see problem 3 before you submit the answer for problem 2. Then you move on. Once you move on, you cannot go back to problem 1 or problem 2. Problem 3 is now your whole world. Do problem 3, then you move on to problem 4, and so on. So you wouldn't be able to skip forwards and backwards from what I remember. There were about 13, 14 problems, somewhere like that. I didn't actually teach 391 in the spring, but I'm just, what I remember other instructors telling me the final was like, that's what it was. For it was multiple choice. Are we talking about the final? Yes, the final is multiple choice. Regrade requests, you can submit those for the test, and whenever I complete the regrade request, Gradescope will send you a message that tells you, oh, your regrade requests were resolved or whatever. For the final, I will have you guys write out your answers and scan them and send them to me after the final. And and yes, I would actually, if you feel like you should be able to get partial credit for something, I will manually handle the regrade requests. Any other questions? Yes. Doing more than 85% of the homework and scoring more than 85 is different. So you do have some leeway with the homework. What it is if your average homework grade is at least 85, I'll automatically give you the extra 15%. So you did all the homework and you didn't get everything right. If you got like an 85.1, I'll give you 100% for your homework grade. So the thing with the homework is I'm kind of giving you 15% of your homework grade for free. Now, I don't necessarily recommend that you not try to be perfect on the homework. You should, but if you're in a situation where you're like, I'm short on study time, this problem I don't think it's going to help me, like I'm just going to forget it. Like you have the freedom to do that. You can do that 15% of the time. Like 85% of the time you need to get through the homework. 15% of the time you're like, I don't feel like it. As long as your study regimen is robust, otherwise you're practicing from the past finals, you're practicing from my practice tests, you're practicing from the textbook suggested problems, you're practicing problems that you should be able to do by hand under timed conditions, then yeah, you can ignore 15% of the homework and it shouldn't affect you at all. But the worse you are at the class, the more you want to kind of be top notch with everything. So ironically, if you're getting, the lower your average grade is, kind of the more work you should be doing inside and outside of homework, if that makes sense. Well, there is a review on the class webpage for the test. So I would start there. I would start, so the general principle would be something like this. Now the specifics might vary depending on the person. But I would, first of all, go through and study all the topics that you know would be on the test, which, as I mentioned, everything since test 1 up to Fourier series. If you have time, study the heat equation. To know the heat equation, you're literally just memorizing that one last formula. It might be worth it just doing the heat equation as well. Go through, make sure you know the general formulas, the general strategies, the general principle. Do you know how to solve a second order linear ODE with constant coefficients? Can you say the steps? Make sure you can do that. Do you know how to find a series solution? Can you say the steps? Do you know what to do first, what to do second, what to do third? Just go through, make sure you know all the topics generally, you know the steps to solve each problem. You kind of have a good handle on it. Maybe practice 1 or 2 examples. Make sure you do know what you're doing. A lot of times students are like, yeah, I feel like I know that, but they never actually verify that they know it. So they tell themselves they know it, but they never actually sit down and do it. So if you told yourself, yeah, I definitely know how to do series solution, sit down, do a series solution problem. Did you get through it, got 100% right, and it was easy for you? Then yeah, you know it. If not, practice a few more series problems, etc. So you're gonna go through and do that kind of house cleaning. General studying of all the topics, memorize everything I put in a box in the notes. Make sure you know that, especially when I put the steps to solve a certain problem. Know that, that's the first thing. Second thing, practice a few problems here or there. Don't spend forever on it, because if you've been doing the homework and all that stuff, you would have gotten some practice along the way already. The next thing is, take the practice test that I posted on the class webpage. Pretend it's a test. That is very important. Get rid of distractions, time yourself, sit down, do it all in one sitting, all at once, where you're doing everything and you're rushing, right? You need to make sure that you know how to do problems under time pressure and under constraints where you cannot use a calculator. So you want to do that. Then you're going to see how you did on that test. Based on how well you did, you might want to do another practice test or just study some specific pockets. So let's say you got a 90% on the test, but 10% of the material you're a little bit iffy on, you can just practice a few problems from that. Let's say you got a 50% on the practice test. Then I would recommend you do an entire practice test over. How? Go to the suggested problems in the text that I gave from the textbook and use the practice test that I gave you as a template. Copy the problems in those positions, do another test. Keep practicing tests. And for the final, the same kind of principle would apply. Now you combine all my practice tests, or you go through the past finals that are on the Math 391 website, and you do full finals in one sitting. Just make sure you can get through a full final, you know how to do everything. Don't tell yourself you know how to do everything. Sit down and do it. Make sure you know how to do everything. Your mind will lie to you, right? It wants to keep you comfortable and safe. It will lie to you. So you'll tell yourself you understand something and you know something when you actually don't. It happens all the time, right? Students are surprised by their grade all the time. So you want to sit down and essentially you want to practice how you want to perform. If you're preparing for a test, you need to do tests. You don't need to look at someone's solutions or watch videos or read notes. If you want to be prepared for a test, you need to do tests. That's what you're doing. So at the end of the day, that should be the bulk of your studying, actually going through practice tests and creating practice tests of your own. To make that more efficient, to make it more feel like a test, get in a study group, create tests for each other. So when you pick a problem and you write it down to put it in a test, by the time you're ready to sit down and take that test, your subconscious was already working on the problem. So it's not a real good model of a test. You want to be surprised by the problem. So what you can do, team up with somebody else, use my test as a template, swap out problems in the book. Don't tell the other person which problems you're putting in. The other person should do the same. Then swap tests and do the test, right? So now you're in a situation where you're practicing how you want to perform, and at the same time, you're surprised by the problems because you didn't pick them. And so it's a really good model of what a test is going to feel like. And also for the final, especially if you don't remember, because you don't want your memory to tell you what to do, you want to actually understand. If you don't remember really what the first test was about or what you even did on quiz 1, you can re-look at the grade scope problems. So go through the grade scope problems and answer some of those. For the, I don't know, I might be able to come with some practice problems for the final, but I'm not going to promise doing that. It just depends on how busy I'm going to be going into next week. So I don't know if I'll be able to create a mock final, but I would, in lieu of a mock final with multiple choice options, the next best thing is to actually go through the long form finals. Go through the practice finals that are on the math department website, and then swap out those with similar problems. Yeah, so I basically just told you how you want to actually take this co-study. Do that. If you get through that process, then whatever your average grade is on that process, that's the grade you can expect on a test. So if you're going through that process and you realize, hey, I'm averaging 90% on all these tests, you'll actually get about 90% in the real test. That's how you know what you know. Anyway, so that was a very long-winded answer, but I tried to be comprehensive. Any other questions? Okay. All right. So I guess we'll wrap up there. Of course, if you have other questions, you can email me. And again, if I didn't get to your regrade, don't worry about it. Definitely before I give you a grade in the class, I'll look over everything that I have to look over. But sometimes it's just hard to, with me having to write tests and prepare for the class, sometimes it's hard to look back at stuff that I've already covered. Okay, so I will see you guys in the future at some point. Test is tomorrow. I'll send you a reminder of the time. Covers everything since test 1 up to Fourier series. It's within your interest to also just look at the heat equation again and memorize the formulas there. It shouldn't be hard to actually do a heat equation problem in the grand scheme of things. We spent a long time up talking about the heat equation, but it's really just the derivation and the thought process that went into the solution. Once you already know that and you know what the solution should look like, it's not a difficult problem to actually solve at the end of the day. All right, so that being said, we are going to stop there. It's been a lot of fun. Hopefully you guys had a lot of fun. Stay safe. Have a good rest of the day. Happy studying. Good luck on your test. Good luck on the final. And as always, I'll see you in the next one. Ciao.